All right, we're back with part two. Example two, graphing probability functions. Well, relative frequency diagrams, and that was, way back in chapter two. One variable stats, which kind of goes with what our review assignment was all about. What is the example? 1,000 fruit flies were monitored for lifespan. Results are given, and a bunch of data. Graph the relative frequency diagram. So notice that this is just the number that number of fruit flies that died in this span, and so on. And we want to graph the relative frequency diagram. So over here, I want the relative frequency. Well, the relative frequency is just the percent of data that fall in each of those categories. Notice there were 1,000 in total here, so this is just 480. Oh, and the numbers are nice. Isn't that fantastic? Just divide this by 1,000. I'm going to get each of my numbers here. That's what I just divided by 1,000. If you're wondering how I got those numbers so fast. And there just aren't many fruit flies that live to be 28 days old, I guess. And I'm going to graph that. So, remember, along the y-axis is the relative frequency. Relative frequency. Along the x-axis is my data, which is in lifespan here. And I want to use a decent scale. Oh my God, we've got to go up to 28, so that's 4 days, then 8 days, 12, 16, here we go. It's not going to look too bad, I think. And then as far as the frequencies, I need to get all the way up to 0.48, so if I go up by maybe that's 0.1, that's 0.2, 0.3. And again, if you pick a decent scale, that'll work as well. So this is the relative frequency, this is the lifespan. And then I'm going to draw a relative frequency diagram. That's the one with the bars, where, remember, polygon? A little bit of exam review too here. Isn't that fantastic? Polygon is the lines, right? The lines. It's the one that looks like that. There's a little thought cloud remembering that stuff from chapter 2. All right, so let me build this. Use a ruler, of course. So 0 to 4, and here is 0.48, which would be up here somewhere. There we go. Maybe color that in later, eh? That'll look great. There's 0.26 around there. Don't have to be perfect, right? The picture's what's worth 1,000 words. Uh, 0.8, there's 0.75, so just above that. Sometimes I miss some. 12 to 16, 0.8, oh, that looks good. 0.30, 16 to 20, 0.30 is just about there. 0.1, almost 0, and I'm going to color this in just a little bit just so we can see it. There, isn't that a fantastic color job? Good enough. Okay, and what's this? This is fruit fly lifespan. Good title. And where are we going? Estimate the probability that a fruit fly lives 6 days or less. 6 days or less. Well, essentially, what it is, it's, where's 6 days? Let me draw a line there. Draw a big red line on 6 days. Nice big fat red line. That's right about, color it. Get a colored line. There we go. Right about here, right? That's 6 days. And anything on the left of this is what we want to count. Anything on the left of this is less than 6 days. Well, all of this stuff, right? All of this stuff here, that's what I want to count. Well, if I wanted to write that in symbols that we're used to, if X is the fruit fly lifespan, then we want the probability that X is less than or equal to 6 days, right? That's what we want using the notation that we just found out. Well, what is it? Well, it's this entire bar here, which is 0.480. There's 48% that were in there, plus half of this bar, right? Half of this bar here. Second bar was 0.26, but half of it, so it looks like around 61%. Around 61% die before day 6, or have a lifespan less than 6 days. Now, one thing I want to mention is this was kind of a probability question that was based on data that were collected. We observed this, but we allowed us to make a probability statement, right? This is kind of like experimental probability, wasn't it? Experimental probability. What would it be like if we wanted to talk about theoretical probability? What about theoretical? Well, essentially, what we'd want is a theoretical graph that modeled this shape of distribution, right? This is just a distribution of probabilities, and I wonder what shape would model that. That goes down very quickly at the start, and then less quickly and evens out like this. It's an exponential graph, isn't it? This is an exponential distribution. Exponential distribution. And in fact, notice that so we look for a model. In this case, it was exponential. And in fact, when we answer probability questions, what we're interested then in, we added up the areas of these rectangles, but when we answer theoretical probability questions, we're interested in the area underneath this curve. That's what we're interested in, and that's what it says in the next slide here. If we know what type of distribution the data has, last time it was exponential, we can do theoretical probability calculations by finding the area underneath the curve. So the big moral to this story is probability is area under the curve. Okay, and what's this all about? This is another probability distribution question. Give the probability distribution for X, where X is the number of times you roll an even number in 5 rolls of a fair-sided die. This sounds exactly like Chapter 7, a Chapter 7 question, right, where it's binomial, 5 rolls, probability of success on each roll is an even number is 3 out of 6, or just 0.5, and the probability of failure is the same, and I want to give the whole distribution. Well, how many successes could I have? I could have 0 successes. I could have 1 success, 2 success, 3 success, 4 success, or 5 successes, where each of these is that formula we just got used to in the last chapter, and it's rearing its ugly head already. And for the first calculation, I'm just talking about 5 choose 0, 0.5 to the exponent 0, and 0.5 to the exponent 5. And you clunk that into a calculator, and you get 0.0313-ish. And then, you know, same thing. You just clunk the rest of these into the calculator. Then x is 1, and you get when x is 1, so that would be one even number that you rolled. You get that, 0.3125, 0.3125, and this kind of makes sense because the probabilities are the same that this is, you know, what's going up and going down, right? It's symmetric, right? So then I'm going to graph this one. And we've done this is just a binomial probability distribution, right? We did this last chapter. Red, nice. Let's try black. It's going to make for a funky graph, that one, but that's okay. What do we want? This is number of successes, number of evens, right? Number of evens here. And this is just the probability of x, and it goes up to 30% about 0.1, 0.2, 0.3, and down here for this one it starts at 0 and then goes up. Got to only go up to 5, so that's no big whoop. And it's going to be symmetric, right? Because we had the same numbers up and down. 0.03 is really small, isn't it? That's 0.0. That's 0.05. 0.03 is maybe there. 0.15 is just about here, right? I want to do a good job of that, so I'm gonna actually make this one green so it looks nice when I do my dots and sticks. 0.31 probability of two even numbers is 0.31. There we go, beautiful. And then it starts going down. All right, and I'll put my sticks in after. Oops. Fantastic. Now that's just review. That's just straight out of Chapter 7. But how does it fit in what we were talking about? Well, one of the ideas is, what type of graph is this? Like what? It's not exponential. It's not going downhill or uphill. And some people say, well, you know what? It kind of looks like a parabola. It kind of looks like it might be a quadratic function. But it's what's weird here is it kind of slows down. If this dot were here and it went down fast, that might make sense. But it's not. It's kind of like it's got a tail here. And in fact, the theoretical graph that this looks like would be if I put a nice smooth curve through all the points. Kind of, oops, I kind of blew that there, but kind of looks like that wasn't very good. Hard for me to. Kind of looks like that, I'd say, eh? And this is a very, very, very important shape. This actually, this nice smooth curve, is called a normal distribution. Normal distribution because it shows up so often in so many normal situations in life. And that's this. Most of Chapter 8 is about this shape. It's also got another sort of layman's terms name, and this, let me give you a hint here, especially around Christmas time, and this almost Christmas time right now, like that. and kind of like this, like that there, and picture grabbing that and shaking it back and forth. This is also called the bell curve. And that's what this chapter is all about. Normal distributions or bell curves would be what this theoretical shape is. Now, what the equation is, well, that's another story. Y equals who knows would be that equation. And that's it. There's a few from the textbook for you to do, along with finishing that one variable stats review exercise. And hopefully you'll get this all done and be waiting around for the next thing to do in class. Have fun with that homework.